It's going to affect, so you affect how much caffeine you intake, and then you observe, does it affect your appetite? That is the dependent variable. Very good. Okay, so now let's talk a little bit about microscopes, because that's going to be our lab activity today. We're going to be working with the microscope. Yeah, we're going to be working with them today. Okay, so this is what most of our microscopes look like. This are a very similar, slight variations on this. There's different parts of a microscope. So we're going to define those parts here in just a minute. But let's first look at the microscope. So a microscope is going to have an eyepiece. That's where your eye is going to go. That's what you're going to look out of. So it's well named. Sometimes they rotate, sometimes they don't, depending on the microscope. The nose piece here is going to be what contains all the lenses, and that's going to rotate. So our microscopes have a 4 times, 10 times, and 40 times magnification. So 4 times being the least, 10 times being the most. You're always going to be able to see something with the 4 time. Depending on what it is that you're looking at, sometimes you won't be able to really make anything out with the 40 times lens, but you'll be checking it each time. When storing a microscope, let's see if these were stored properly. No, not always. Colors also go with the lenses. So the red lens, or red line lens, that's going to be the 4 times. 10 times is yellow. Blue is going to be the 40 times, or the highest. So there's a little band with those colors. When storing a microscope, you're always supposed to store it on the smallest magnification. And the reason for that has everything to do with the stage. Because the stage is never going to touch the 4 times because it's the shortest. But if you leave it on the 40 times, you can actually crush the lens by moving the stage up too much. So you always store it, or are supposed to store it, at 4 times. You have, actually, I'm just going to keep this, except I'm going to grab this one. So the stage is the platform on which you're going to place a slide to view. And you have these stage clips, which are going to hold the slide in place so it doesn't move around when you are looking through. The diaphragm is this wheel underneath the stage, and the holes on the diaphragm vary in size to adjust how much light is going to come up through the stage. Also, sometimes there's different filters on there depending on the microscope. Sometimes there's a blue lens, sometimes there's a red lens to kind of color the light differently. This can help with clarity depending on the color of the sample that you're looking at, if it's stained or not. Then you have 2 types of adjustment. And depending on the microscope that you have, although most of these, actually there's only one of them that has it separate. There's usually a coarse adjustment and a fine adjustment. Okay, the coarse adjustment is going to be the bigger of the 2. And it's going to move the stage in big ways. The fine adjustment is located on the coarse adjustment, and it moves the stage in smaller ways. When you are set at the 4 times magnification, this is important, so if you're not paying very close attention right now, tune in. You only use the coarse adjustment at the smallest magnification. Or, yeah, no, the largest magnification, the 4 times. So it's not well, how should I say that? You only use it at the 4 times. So it's not magnifying things the most. It's magnifying things the least because it's only magnifying it 4 times. 40 times would be the highest magnification. So you only use the coarse adjustment on the 4 times. And you get something into focus at the 4 times. So you get it focused so you can see it. Then you move up to 10 times and you use the fine adjustment to refocus. Because once you move up in magnification, it's going to get blurry. So then you use fine adjustment to refocus. The error that a lot of people make is that they will use coarse adjustment then to get themselves refocused, and then you get lost. Then you get lost trying to, you've moved the stage too much, and you get lost trying to get it refocused. Don't use the coarse adjustment except for at 4 times. Once it goes up to 10 times, you use the fine adjustment. That will help you be able to find things more easily. It's a learning curve. It's always a learning curve with microscopes, but it will help you have an easier time with it. You aren't in danger on the 10-time magnification, the yellow magnification, of crushing any lenses with the coarse adjustment, but it's just easier to only use the fine adjustment at that level. Once you go up to the 40 times magnification, the blue, then you're in danger of crushing the lens if you use coarse adjustment. So coarse adjustment on the blue line is a no-no. It's a no, don't do it because you can crush the lens. So that's a bad thing because it will go all the way up to touching the stage. So that's kind of just a little bit of instruction on how to go up in magnification and have the easiest time. All of our microscopes have a light source. They are a light microscope, so they have a light source at their base. Most of them also are going to have a dimming switch that allows you to adjust how intense the light is. When you're at the lowest magnification, so when you're at 4 times magnification, if you have too much light coming up through it, it can be kind of blinding. So usually you want it a little dimmer. And then as you increase your magnification, you usually need to increase the amount of light that you use so you can see things more clearly. Okay, so now when you have in a normal microscope, a normal light microscope, compound microscope, which is what these microscopes are, you'll always have a gap between your slide and the lens. There's always going to be a gap. It might only be a small gap if you're at the highest magnification, but there's always going to be a gap of some sort. That's not the case with all microscopes. In order to see the smallest things like bacteria, you actually use, which we don't have these, this would be if you take a microbiology class in college, something called an oil immersion microscope, where you actually use oil on your slide and it touches the lens. So it gets so close to the slide that it's making contact pretty much almost with the slide, so you have to be very careful, and you use a drop of oil. Why? Why do you use a drop of oil? Does anyone have any guesses?
Liquid magnifies.
Okay, liquid magnifies.
So it won't scratch the lens.
So it won't scratch the lens. Both of those are really good answers. And you know what? Each of those might play a factor into it, actually. Yeah?
But isn't the oil going to distort the image that you see?
Actually, it makes it more clear. So what the oil does when looking at really, really small things, so we're talking about bacteria cells, which are tiny, 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 tiny. It keeps the light from scattering. So here, the light, see the big way it fans out? What the oil does is it actually focuses the light on the lens and keeps it from scattering so that you're actually able to see the bacteria. Otherwise, with a normal light microscope, you can see bacteria, but not very well. And we'll look at some bacteria slides here in a couple weeks. But you have to have colonies in order to see them. You can't see individual bacteria very well. And the last type of microscope, so we have a compound light microscope, which is like what we're using. There's an oil immersion light microscope, which looks actually a lot like ours, only it has an additional lens specifically for oil immersion. And then there's the electron microscope, which obviously we're not going to be using these. Electron microscopes actually scatter electrons so that they smash into a substance, and the wavelength that they release when they smash into that substance is then captured and an image is created on the screen. It's like crazy stuff. Crazy stuff. But the images have incredible clarity and allows you to see it allows you to see small things very, very well. So this right here, this is a fly. Isn't that crazy? Like when I look at stuff like this, I'm like, that looks alien. Like if that was as large as a deer, that would be very scary. Like because it's a fly, it's okay. But if it was like even the size of a bunny rabbit, even the size of a mouse, that would be frightening. That's what I feel like about some ocean creatures, which are kind of creepy looking like that. But that would be quite frightening. This is bacteria. So this is an electron microscope of bacteria. So different shapes that they take, and these ones are kind of adhered to each other in a colony. Yes. So usually, most of the time in electron scanning microscope, things are in grayscale, and then they will add color to show different types of things. So they'll add that in post-production, I guess, or something, whatever you want to call it. They'll add it after the fact when printing the image or showing the image. This right here, this is the coronavirus. So that's a scanning electron microscope image of the coronavirus. Gets its name because of the crown that it looks like it's wearing around it, I guess. Corona. And these are blood cells. So here we have red blood cells, white blood cells, some little platelet fragments up in here. So that's what's floating around in your blood. Okay, let's see here. Said everything I wanted to about that. So we're going to play another short video on the microscope before I introduce our lab activity. The tube that changed the world. It's very, yes, please. Epic name.
It's the very symbol of scientific endeavor used by researchers in most every field, whether you study elephants or nanobots. If you do science, you probably need to study the very small before you can get to the big picture. For more than 400 years, we've been able to do this thanks to the optical or light microscope, an ingeniously simple device without which we would not have found a cure for polio or been able to make microchips or discovered some of the fundamental properties of light itself. And it made it all possible using the same basic technology for hundreds of years. Of course, if you want to start a full-on petri dish, throw and roll up your lab coat sleeve science fight, all you have to do is raise the question of who really invented the microscope. Some like to attribute it to the guys who pioneered the telescope, like Galileo and Hans Lippershey, both of whom tinkered with using lenses to get a closer look at things here on Earth. But many give credit to the Dutch father and son team of Hans and Zacharias Janssen. In the late 1500s, they were making their living as eyeglass lens grinders at a time when eyeglasses were like the Google Glass of the day. It was cutting-edge stuff, and everyone wanted it. Especially people who couldn't see. But the Janssens wondered what would happen if you took a telescope like Galileo's, which had a really big concave lens on one end to gather light, and a convex lens on the other to magnify it, and instead used two very small, almost spherical convex lenses. They found that their device could magnify objects up to 9 times, and it had a short focal length, meaning it could bring images into focus over a short distance. This was pretty handy for their extremely nearsighted customers, but their contraption's usefulness for scientific research seemed to have largely escaped them. It was 70 years later when English philosopher Robert Hooke tricked out the Janssen's design and used his own version to study the natural world. He scrutinized the structure of feathers, the eyes of houseflies, and perhaps most famously, thin slices of cork. The tiny compartments that he saw in the woody tissue reminded him of monks' chambers, and he named this essential unit of life after them, cells. But then, scoring another win for Team Netherlands, Dutch polymath Antony van Leeuwenhoek soon designed his own handheld microscope with new special lenses that could magnify objects up to 270 times. And suddenly, a whole new world was opened up to human eyes for the first time. Leeuwenhoek discovered organisms that no one had any idea even existed, like bacteria found swimming in rainwater and human saliva, which he called animalcules. He also observed microscopic nematode worms, tiny waterborne rotifers, and was the first to observe human cells, like red blood cells and sperm. Our understanding of the world around us would never be the same, and with each new generation, the microscope took on new modifications to make it sharper, more stable, and more powerful. By the late 1800s, we arrived at a version pretty similar to what you know today, with a stage for holding your specimen, a light source, usually underneath, followed by objective lenses that collect and focus the light coming through the specimen, and an ocular lens, or eyepiece, that magnifies the image. This simple setup and the window onto the world that it opened got to be so essential to scientific pursuit that microscopy soon became a kind of science of its own. And any discovery that cracked that window open just a little wider got you a Nobel Prize. Like in 1926, Austrian chemist Richard Zsigmondy broke the code of how to study particles smaller than a wavelength of visible light by inventing the ultramicroscope, which aimed a high-powered light beam at an angle through a colloid of particles. Nearly 30 years later, Fritz Zernike won the Nobel Prize in Physics for inventing the phase contrast microscope, which finally made possible the study of colorless and transparent materials. And we're not even talking about the whole new wave of technologies that the optical microscope inspired, like the electron microscope, which uses beams of electrons instead of light to magnify images up to 10 million times, or the scanning tunneling microscope, which can resolve surfaces down to the atomic level. Science is amazing, and much of it is made possible by revealing what once had been invisible, and we'd like to thank Subbable subscriber Labverse, which aims to let people explore the invisible world via a remote web-based microscope, for choosing this topic. If you'd like to choose a topic for a SciShow episode, or sponsor a graphic, or get your own personalized SciShow lab coat, go to Subbable.com.
Now he's just advertising stuff. Okay. Okay, so let's take out those sheets that, or it's probably out. We're going to go through and define these terms. Different parts of the microscope. So starting with, it's located on the side of the frame. I don't actually have this sheet. I have the answers. Located on the side of the frame, used to adjust the focus of the microscope. This is the adjustment knob. So if you didn't already put that in, it is the adjustment knob. It supports the upper part of the microscope. This is the arm of the microscope. It's also how we carry the microscope. It's located on the stage and adjusts the amount of light that passes. It's the diaphragm. So the bottom of the microscope, and it's used for support. That is the base. It supports the microscope. It's a light or mirror that projects light through the diaphragm. This is the light source. Okay, all of ours have a light on them, but some microscopes have a mirror that you have an external light source, like a flashlight or something, and you catch the light with the mirror and focus it. The light or mirror that projects light through the diaphragm. Oh, oops, I already said that one. Okay, connects the eyepiece to the objective lens. That is the tube. Holds the slide in place on the stage. Those are the stage clips. The lens or system of lenses in a microscope that is nearest the object being viewed. Those are called the objectives. So the objective lenses, those are the ones that are in 4, 10, and 40 times. Holds 2 or more object lenses and can be rotated. It's the nose piece. Combination of lenses at the viewing end of the optical instrument. That is the eyepiece. So there is a lens here. This technically does come off. Can either lower the magnification or increase it. Some of them have lines on them, so don't be freaked out by that. There's like a needle. That's so that if I wanted to come around and like get it centered on something to show you. So don't be like, there's this line, what is that? It's meant to be there. And then, last one. The small platform where the specimen is mounted for examination is the stage. So those are the pieces of the microscope. Now we've gone over how you move up your objective, or how you can move up the different lenses. So it's easiest to kind of put both of your thumbs on the stage clips and then use your pointer fingers to kind of slide whatever slide you are looking at, and then let the stage clips down to fix it in place. It's also best to use the coarse adjustment knobs to get the stage to be as low as it can be before you start playing with the lenses. You obviously have to turn the light on. Some of these have two light sources. They have an upper light source and a bottom light source. You want the bottom to be lit up, not the upper one. That will flood things out. There's certain scenarios where that's helpful. Most of the time we just want the bottom one lit up. Then you'll use the adjustment knob. Doesn't really work well with my face shield on. Then you'll use the adjustment knob to get your slide in focus, and you can use the coarse adjustment knob at the 4 times. Once you get that in focus at the 4 times, you can move up to the 10 time and use the fine adjustment knobs, see what you can see. Then finally move up to the 40 times, use the fine adjustment knob, see what you can see. Remember that you can adjust the amount of light that's coming in and out, both with the adjustment knob for the light and then also with the diaphragm. That will change the size of the hole which the light is coming through. So both of those are ways that you can do that. Now most of your slides you're going to analyze, and you'll be able to come up and choose 3 slides of your choice, and you'll be taking some notes on those slides. So what I want you to do on this side of the lab is you're going to have 3 different objects, 1, 2, 3, and then you're going to, for 4 times, 10 times, and 40 times, to the best of your ability, I realize this isn't an art class, draw what you see. And use words to describe it. It looks like squiggles. They're like tiny little circles connected by mush. I don't know. Describe what you see. It doesn't have to be like super scientific sounding. Like, describe what you see. That is science. Scientists don't always sound super sciencey. If you could read their journals of like when they're taking notes on stuff, I'm sure we would probably chuckle at some of the observations they make. So you're going to do that for 4, 10, and 40 times on 3 different slides of your choice. Then on the back side, you're going to be preparing what's called a wet mount. So you're going to come to me when you get to that point, and I have a red onion, and I'm going to shave a very small piece of onion off for you, and I'm going to put it on a slide, and then you're going to take that slide, and you're going to take an eyedropper, like they have right here, and you're going to put a couple drops of water on the piece of onion, and then you're going to take this cover slip, which is this very small, flimsy piece of glass, and you're going to cover the onion and the water with the cover slip, and then you're going to look at the piece of onion through the microscope. So that's called a wet mount. Now you can use something that is no longer living, like the onion, because it's now been plucked from the plant, so it's no longer living. Or you can make a wet mount out of like a drop of pond water. When you go to put the cover slip on, your goal is to try and not get air bubbles. And how you do this is you create like a hinge point with the cover slip, and then you slowly, so you don't just come in straight down and plop it on, but you create like a door, like you pretend that it's a door opening and closing, and then you gently hinge it down and drop it. And that will create less air bubbles. I won't promise you won't get any, because it is one of those things that there's some finesse to, and it requires some experience sometimes doing that, but you will try with that. So this is what we're going to do. we need to be in lab groups of no more than 3. So this table here will be a lab group, and your table only has 3, so you'll be a lab group. And then, okay, I have 2, 4, 6, 8. I think I have 8 microscopes with me. So let's go with two at the end, Macy and Sophie. Samantha, if you'll join them. And I'll actually have you guys go into the kitchen, and I'll bring you a microscope in there, because it'll be one of the ones that needs power. And then we'll have, let's see, so then it'll be you three, and then we have, do I have, oh, I don't, there's one person missing today. So we can do, that's 1 microscope, 2 microscopes, 3 microscopes, 4 microscopes, 5 microscopes, 6. I'm going to have you two, we'll do a microscope here, and we will do a microscope. Why is this so hard to figure out? Because some people are sitting in 3s and some people are sitting in 2s. Actually, I can stop this now.